Properties of polylogarithm function under differentiation and integration. So basically in my previous videos I've already defined what polylogarithm function is and its integral representation. You can check the video over here. So there I did tell that the polylogarithm function base s of g is defined as the sum going from n equals to 1 to infinity, and there we have g to the power n by n to the power s. And I also told about the integral representation of polylogarithm function, which is 1 by gamma function of s, integral going from 0 to infinity, t to the power s minus 1 by e to the power t by g minus 1 dt. Okay, so these things need to be in hand, and now we will begin exploring its properties under differentiation and integration. So now for the first property, we can just first differentiate a polylogarithm function and then see what happens. So we'll basically use the sum formula. Now if we differentiate polylogarithm with respect to g, because there are two variables involved, s and g, that's why I'm using a partial differentiation so as to mark s as constant. So if we differentiate, we get sum going from n equals to 1 to infinity, yeah, and then there we will have n g to the power n minus 1, and since it is a partial differentiation with respect to g, s is a constant, also n is a constant, so n to the power s remains as it is. So this changes to sum going from n equals to 1 to infinity, yeah, and then g to the power n minus 1 by n to the power s minus 1, yeah. Now we can take g to the power minus 1 outside the sum because sum is in the world of n, yeah, that's why we will have 1 by g sum going from n equals to 1 to infinity g to the power n by n to the power s minus 1. Now this is just the polylogarithm function of base s minus 1 for g. Yeah, you can get that from the sum definition. Basically, if there's s, we have s. If there's g, we have a g. We have a g, but we have s minus 1. So now after this, we know that this is partial differentiation of polylogarithm function with respect to g. Yeah. Now we can take g to the other side, and we'll get g times partial derivative of polylogarithm function with respect to g, yeah, and this is polylogarithm function base s minus 1 of g, and we prove the first property. After a few minutes we'll also use this property to find different special cases, yeah, but for now, yeah, we have found this one, the first property. Now let's go to second one. For second one, we will use the first property itself. So let's see how we do that. We have partial derivative of polylogarithm function as li of, let's say if there's s plus 1, we will have lis of g by g. Yeah, is it? Yeah, just take g to other side. Now if we integrate both sides from 0 to g, yeah, what do we get? And with dz over here, now for this the dz cancels out, so we have the derivative of this thing, and that will just be lis plus 1, yeah, as an integral. It comes out like this, and it's going from 0 to g, yeah. Over here we have integral from 0 to g lis g by g dz. Now when it's g, we evaluate this function at 2 points. At g, this is just lis plus 1 of g, and at 0, if there's 0, if we substitute 0 in the sum, we will just get 0. Yeah, so that's why we can write this as lis plus 1 of g minus lis plus 1 of 0, and this is integral from 0 to g lis g by okay, g dg. Oh yeah, now basically I think that I could have written this okay, fine, now this goes to 0, but I think like from okay, but what I think is, so basically if the partial derivative goes outside the integral, we will have d dz of integral from 0 to g of lis plus 1 g dz. Yeah, now from the fundamental theorem of calculus itself, this should be just the lis plus 1 of g. Yeah, and this way also I think it's true. Okay, let's do it. lis plus 1 g, and then we have integral from 0 to g lis g by g dg. Okay, so we have got the second property as well for the integral. Yeah, so integral from 0 to g of lis g of by g dg equals to lis plus 1 g. Now we'll use this property to find some of the special cases. So basically the one of them we already know from the sum itself, because lis of g is equals to sum from n equals to 1 to infinity of g to the power n by n to the power s. For s equals to 1, we can already find that because that's a well-known sum. Yeah, g to the power n by n, and this is just minus ln of 1 minus x. Yeah, we do know that. Now if we want to find li0 of g, let's say, so for that what we can do is, if we take g times partial derivative of li1 of g, we know that we are going to get li base 0 of g. Yeah, that's why let's do that. We have g, and if we differentiate this, we have minus 1 by 1 minus x times minus 1. So yeah, we got the li0 of g. Okay, not x, this is g. So that's why we have li0 of g as g by 1 minus c. Now let's say we want to find li minus 1 of g. Then we will have g times, now if we see such terms in integral, we can directly write li0 of g, and the further manipulations can be easier. So that's how it can help. And if we take li0 of g, we know that we are going to get li minus 1 of g. Yeah, and that gives us g. Yeah, and now if I differentiate this, that will be 1 minus g times 1, yeah, minus g times minus 1 by 1 minus g whole square. Yeah, this is li minus 1 of g. So this is now 1 minus z plus c, so 1 by 1 minus g whole square. This is li minus 1 of g. Yeah, and yeah, we got the value for li minus 1 of g as well. Yeah, now what about li2 of g? Now what about li2 of g? For li2 of g, we know the integral thing. Yeah, okay, so if I want to find li2 of g, what I can do is, I can integrate from 0 to g for li1 of g by g dg. Yeah, now what is li1 of 1? Integral from 0 to g minus ln of 1 minus x by not x. Why am I writing x over here? This is g actually. Z by z dz. Now this is li 2 of g, yeah. And this integral is really like troublesome to evaluate, but we do know that this integral is li 2 of g, and that's why we can also write this as sum, and that's how these things are helpful. And these things also have many other properties and many other manipulations which simplify the integrals in many ways. We will also see few problem solving in our next video. I will link here. Yeah, so basically for now let us see how this integral can be changed to sum from n equals to 1 to infinity. Since we have s as 2, we have g to the power n by n square. Yeah, so this is this integral in summation form. Yeah, and now we have found li2 of g as well. So we have found pretty much many li base s, and these all of these have been possible due to these two properties. And now hope you have known how these properties are derived, yeah, and how these can be helpful to find different bases for s. And yeah, that is it. I hope you enjoyed the video. Look forward to seeing in the upcoming videos too.